All good. So thanks to Mark and the sponsors for hosting the event, and to everybody for coming out. It's great to have heard from so many that are supportive of the intersection of science and commercialization of space. So, quick intro to myself. Before I started Phase 4, I went to the University of Michigan multiple times for, go blue? Yeah, all right. For a couple degrees in aerospace engineering and master's, an MBA. And I started my career at Ball Aerospace, working on the New Horizons mission, which just passed Pluto. And later on, I joined Northrop Grumman as a systems performance analyst and eventually became a team lead of satellite development in 2012. I was one of the first business development folks with a technical background that worked at Spire, which was known as NanoSatisfy in 2013. And as was mentioned, I guess this makes me a serial entrepreneur. This is the second company I've started. The first was Ether Industries. It was a high-altitude balloon company, started in about 2014 and acquired in 2015. And all of these experiences culminated in, no pun intended, the next phase of my career. I saw where the industry was going. I saw big satellites getting smaller. I saw people wanting more access to space. And from my perspective, I think the costliest barrier facing this widespread adoption and exponential growth of satellite constellations is the propulsion system. So looking back at some of the folks that spoke this morning, and I know there's some logos up here I haven't added, but envision them up there. Before I dive deeper into Phase 4's role in the commercial space race, I think it's worth looking back at this morning, and maybe one key takeaway is that you see a lot of rocket companies and you see some really interesting satellite companies starting to take shape. But it's not just about access, but about transit in space. So it's not just about getting to the port, but it's about going from the port to your house, or from the port to the store where whatever is going to be sold. So you see this in a number of endeavors. I think Blue Origin and NanoRacks kind of taking that payload from Earth into space and then moving it around, or allowing folks to test is a good example of the positive commercial partnerships that are instrumental in building a larger space ecosystem. But again, we see a lot of headlines about rocket companies, but I think it would be fair to say that a lot of the data, a lot of the science from space does not come from the rockets. It comes from the satellites that we put in space. There was a great illustration of, I think it was that LISA mission with the triangle of 3 satellites, hundreds of thousands of miles away from Earth, the first presentation. So anybody recognize this logo or this drawing here? Anyone? This is MMS. I'm going to read NASA's description of it because it's perfect. So MMS is the Magnetospheric Multiscale Mission. It's a set of 4 satellites that are, these are in space right now, 4 satellites that are examining how the sun and Earth's magnetic fields connect and disconnect, explosively transferring energy from one to the other in a process that is important at the sun, other planets, and everywhere in the universe, known as magnetic reconnection. Reconnection limits the performance of fusion reactors and is the final governor of geospace weather that affects modern technological systems such as telecom networks, GPS navigation, and electrical power grids. So these 4 spacecraft measure plasmas, fields, and particles in a precise but rarely used and relatively hard to access orbit. They're not just in low Earth orbit. They're moving between where the Earth's magnetic field intersects the solar wind, and then on the tail end of that as well. So it's a pretty crazy, funky-looking orbit. And so now, from my perspective, let's take a closer look at the MMS satellites. Again, there are 4 satellites that are identical. I think they're about maybe 2 or 3 meters in diameter for some perspective. So what takes up the most room on this satellite? Anybody know what the big red things are? Propellant tanks, right. So maybe ask yourself, with your scientist hat on, what would you do if you had a propulsion system that was 5 or 10 times more efficient? Would you use smaller propellant tanks, maybe lighten up the satellite, get a cheaper mission? Maybe you'd add additional science payloads in. Food for thought. So a lot of the data we initially collect in the name of science eventually gets commercialized in some form. So weather satellites are still taxpayer-funded assets, but now there are a number of companies, Marco mentioned one, that are getting into the weather business. And so what happens when a satellite like MMS, or a constellation like MMS, starts to unlock the mysteries that affect power grids and telecom networks? So let's take a look at what's going on in space from the propulsion perspective. But I'm going to try and tie it into a terrestrial example. Looking at the last couple centuries on Earth, pretty much all people and products go from point A to point B via multiple modes or methods of transportation. To get here today, I took a ride share to the airport, I took an airplane from LAX to JFK, and then I took another ride share here. So I've got all these options here on Earth. I could have taken the subway today, I could have taken a helicopter if I could afford it. We've got boats, trains, trucks, drones, etc. But in space, it's kind of a different story. We've got some incumbent systems. These are pictures of systems that have flown in space. Some of them are absurdly expensive. Some of them are just incredibly complex, take too long to build. Some are just not that efficient. Some are just hard to manufacture, and they can't really keep pace with the rapid changes we're experiencing today in space. So you end up with sort of an artisanal onboard propulsion system to get to your ultimate destination. It would be like building a new engine for your car to go to the grocery store and then building another engine to go to drop your kids off at school. It doesn't really make sense, and it sounds expensive and time-consuming. So as we expand in space from science into commerce, I think there's a growing need for new propulsion systems that offer what we call last-mile maneuverability of space vehicles and satellites. A little bit about Phase 4. The propulsion systems like ours represent the most cost-effective way to add maneuverability capabilities to the broad suite of satellites that are heading up into space. So new maneuverability translates to higher quality monitoring, higher quality defense uses, collision avoidance of other satellites and debris. And the inexpensive nature of our system lends itself well to scientific applications where budgets can be constrained, as I'm sure some of you have experienced. But propulsion precision is paramount. Say that 3 times fast. All right, so a little bit about the system. It's a powerful electric propulsion system, simple design, and that simplicity lends itself to scalability. So it's the smallest plasma propulsion system available today. It can be scaled for use from a CubeSat to a small satellite and even to large satellite constellations. Our thrusters, like some other electric propulsion systems, use plasma for thrust, but what we've done is removed some of the extraneous and failure-prone parts like electrodes and high-voltage electronics that add complexity to more traditional systems. And without revealing too much of our secret sauce, what we basically do is use components that are similar to what you find inside of a cell phone or a wireless charging mat. And we're able to excite and direct plasma using those technologies to translate into powerful and dynamic maneuverability. And because of the way our technology works, our thrusters are on the high end of the thrust spectrum for electric propulsion. So that means you get to a final destination to collect scientific data quickly. And then the fact that we're electric means we're also efficient, so that when you get to that destination, you can dwell there for a long time and start turning data points into data patterns. Couple examples. I think we have a great chance to win contracts that provide for broadband access to the world, for constellations doing all sorts of interesting scientific things. All of these types of constellations require propulsion. And of course, imagine if you could shrink down those 4 red tanks and maybe put a couple smaller tanks elsewhere in the spacecraft and what you could do with that additional space from a science perspective. So a lot of folks started with the vision of their company. I'm going to end with mine. So while we're a commercial business, I founded the company on the vision of orbiting every planet and every moon every day. And it's therefore our mission to accelerate the democratization of space by building the best electric rocket engines. And so of course, we cater to the new private space industry, companies like Astro Digital. We just announced a contract with them. But our vision dictates and mandates that we have to appeal to the more traditional public scientific industries, such as another newly announced contract with NASA. So we're very aware of what you folks are doing. I, of course, want to hear a few more questions. So by building these engines, we're aiming to solve that last mile part of the intermodal transport equation in space. And I appreciate the opportunity. I've got some time for questions. One food for thought question, maybe throw out some answers. Where would you go if you could go anywhere in space? Thank you.
There's quite a few different electric propulsion systems out there. There's Hall thrusters, fascinating. That's not been done yet. But
yeah.
What's the difference between yours and the plasma? I mean, what kind of ISP? What's the trade-off for thrust?
Good question. So the question is, what's the difference between our electric propulsion system and other electric propulsion systems? So let me actually I'll show you our system here. Well, here, so you can see in the two on the left and right of your screen, you see a Hall thruster and a gridded ion engine. So, and you also see in the center of the Hall thruster, which is, I guess, on the left, and the ion engine on the right at the top, you see an extra little point of light. That's an electrode that, or a cathode rather, that will neutralize the plasma. So we've removed that piece of additional extraneous equipment. You can see that here. There is no additional point of light. What that system does is neutralize the plasma. Our plasma is self-neutralizing. So you don't need those additional parts to take the positive ions that build up a charge around your spacecraft and neutralize them with electrons. We do that in a single flow. So that means you get a smaller system that's just simpler with fewer parts. We also don't use high voltages. So imagine what's going on inside your cell phone is you're converting battery power into radio waves. We're doing the same thing. We're taking battery power and converting it into radio waves that excite this plasma. So these other systems use a much higher voltage way to do that. We use a lower voltage system, which means it can go from something the size of a tower computer to something the size of a cell phone to handle that kind of power.
Chemically based rocket engines have a figure of merit called specific impulse or density specific impulse, and it's relating the efficiency with which the rocket engine converts chemical energy of the propellant into motion. What is the appropriate figure of merit for an electrically driven system? And based on that metric, how do you compare it to other electrically based propulsion systems?
This is something we argue about, and depending on who you're talking to, investor or customer or whomever, there's a number of different answers. And thanks for reminding me about specific impulse, which was another question. For some sense of scale, the MMS mission, I think, uses a monopropellant thruster, which is about 200 seconds of specific impulse. We're targeting 1,000 to 1,500 seconds, so 5 to 7 times that amount. So that's the impulse question. The one figure of merit we like to use is impulse per watt. So how many seconds of specific impulse can we deliver per watt of power you give us, which is another way to look at efficiency, electrical efficiency, et cetera. And so when you look at the performance of our system, you find that you're roughly on par with a Hall thruster or an ion engine. So you're something like 6.5 seconds of specific impulse per watt of power. And so as far as performance goes, we're kind of on par with everybody else, so we try to differentiate ourselves by being a lower cost, yet more reliable option.
I've heard more than a few people mention the phrase democratization of space, but I'm a little bit skeptical about that idea because not everybody on this planet has the same access to resources, etc. So what is that? What does that really mean? And how do you see all of us getting there? Or what does that look like?
We're building that. I think the way that Blue Origin and SpaceX are doing it from their perspective is providing that first access point, lowering the cost 10x, and from there you can build systems on top of that can continue to lower the cost. Just for some reference, and somebody earlier pointed out that you can't necessarily use the past to predict the future, but space used to be the purview of governments alone. You had to have government money to do anything in space, and now if you can afford a Ferrari, which is more people than before, you can basically do something in space. Or if you can convince people that own Ferraris to lend you some of that money, maybe give up a Ferrari, you can basically get to space. So that we're on track towards democratizing that, and it doesn't come from just a single solution like one great rocket that lowers the cost. It's a combination of the rockets and the shrinking of electronics and the democratization of information available on the internet. That information of how to do it is out there. So we're playing a part moving you around, and I think others are going to build on what Blue is doing, what we're doing, and what SpaceX is doing to lower that cost, to allow those millions of people to be living and working in space. Or the fact that we all use GPS today is evidence of some democratization of space. We all use that, whether we know it or not. If you got a cell phone, you're using GPS.
And just to follow up on that, I think we see with science in particular, and in this conference's discussions, the gatekeepers are changing, right? You had to write the proposal to one entity, your National Space Agency, and they were the only ones who could open the doors to you. And part of what democratization means is that there's different access points. It's not everybody, but it is anybody.
Okay, so
Thank you.
First, second, third.
Yeah, big fan of the word democratization. But last night I was flying in here, and there was this group of students that were actually sending an interplanetary small sat out. And for me, it's Venus and Enceladus. I was wondering what form factor do you think you could put your thruster on for the small sat?
So the question was, what type of form factor could the thruster get put into? And I assume you mean with fuel tanks. And you'd be to go to Venus or Enceladus. There's a couple different approaches you could take, and there's trades with architectures. People talk about maybe like what's happening to Mars. You've got kind of a mothership, and then the InSight, and then the two Marco spacecraft. Generally speaking, so electric propulsion. We're high thrust for electric, but we are still low thrust relative to a big chemical system. So you could do it with let's just call it an ESPA class, which is about 100 kilogram satellite, maybe less, because you've got to also think about power and communications and maybe larger solar panels and a long duration burns. So the form factor of the thruster, I'm not going to do the math off the top of my head, but is something about the size of a dorm room fridge would get you to, with our thruster alone, probably from Earth orbit to another planet in the sort of middle inner solar system.
Could you bring back the slide that would show the MNS constellation? All right, so is this a set orbit? Could you just do this one more time? For those of us who are not rocket scientists.
Yes. Sure. So what you see on the right is representative of the magnetic fields of Earth. You remember from school, the magnetic field lines come out of the top, the North Pole of the magnet, and then reconnect at the South Pole. So those extend into space hundreds of thousands of miles. And so at the edge of, sort of in the middle here where the colors get pretty fun, is the meeting of the solar wind, so highly charged particles coming off of the sun at high speed, meeting with the Earth, the kind of the edge of the Earth's magnetic field, and causing some disruptions, which it's sort of depicted in the drawing, disrupt things like communications or even power grids here on Earth. Does that?
I'm with you there.
Okay. So the satellites are basically flying through that intersection. They're flying through where the sort of the red and the green meet, and then you don't see it in the drawing, but on the other side of the Earth, there's like a long tail to the magnetic field. So they're flying in I guess it would be a pretty highly elliptical orbit, well outside of even geosynchronous orbit.
Okay, so since it's based on solar wind, it's fluid.
It's
Not
fluid.
a set orbit.
Oh, correct. Yeah, it is. That's right. Yeah, you're not dwelling there, but you're continuously moving through the same point. Yep.
So we had one last question, yes?
So can you talk a bit about some of your recent purchases of space force? I know I think NASA just a few days ago did something.
Yeah, the question was just about some recent purchases. So we've had interest from the commercial and the government side. Also, a lot of scientific interest, but sometimes that doesn't necessarily come with the funding. So we're trying to work with partners to find a way to make that happen. But Digital is a commercial data company, so they gather hyperspectral imagery. So think about Planet Labs, you may have heard of, or Digital Globe gathers visual imagery. Digital gathers imagery outside of the visual spectrum for big agriculture uses, and then NASA using it as a technology demonstrator. This is the only RF thruster of its type or RF thruster that's flight ready. So NASA wants to see if we can basically, get more CubeSats up and keep them up longer. They want to see what happens when this thing actually operates in space.
Thank you very much.
Thank you.
Can we give a hand to everybody who was speaking in this session? I think it was very nice.